Many of the planet's greatest railways have inspired great engineering in order to conquer its harshest terrain. But whether carved through vast mountain ranges or cut through impenetrable jungle, arguably any railway's most impressive feat is bridging nature's great divides. From deep river gorges to wide open seas, our railways cross seemingly impossible chasms, connecting both communities and countries. But each of these crossings create engineering challenges that could stop a railway in its tracks.
This is the Mahaka River, and when you look up, you get a really good sense of the huge challenge that the engineers face.
This stretch of water is quite long. We have 16 kilometers from Denmark to Sweden.
You can see it's a very huge valley, and the valley sides are very steep.
It was one such problem facing railway engineers in the US over half a century ago. If you're an island city separated from the mainland, bridging waterways can allow rail supplies to flow, but can leave your vital rivers well and truly blocked. Keeping everyone happy in the city, hey, come on, can be an all but impossible bridging challenge. But one railroad in 1950s America proves otherwise. Staten Island in southwestern New York. Sandwiched between mainland New Jersey and Brooklyn, it's a critical gateway into this busy metropolis, one which trains must access. Today, alongside tons of cargo, Professor Eric Lima is experiencing an unrivaled view of the railway.
Oh man, we're on the front of a diesel train right now. The power on this thing is amazing. This freight service is huge for New York.
But getting locomotives into Staten Island means overcoming a tricky geographical problem.
It's the artery that brings all of the goods and services that we use on a daily basis, and we don't think about it when we're in the city, but New York City is completely surrounded by water. So for trains, this is easier said than done.
The stretch of water separating Staten Island from New Jersey, known as the Arthur Kill, may only measure around 170 meters across. But it's packed with boats.
This is an extremely busy waterway. There are thousands of boats that go through. And if you're going to have a railway across, you're going to have clearance for those boats to go under.
For a pedestrian or a car bridge, getting this clearance is no problem, as rubber tires and grippy soles can cope with an incline. Whereas steel-wheeled trains faced with a quick ascent get themselves into a spin. However, in 1959, the Baltimore and Ohio Railroad got round this problem with a monumental solution.
Wow, this is amazing. It's the world's largest lift bridge, the Arthur Kill.
But it's this bridge's extraordinary actions, rather than its colossal scale, that makes the Arthur Kill Bridge a standout structure.
I mean, that's an engineering marvel.
With a lift span of 170 meters, the Arthur Kill is the longest single-span vertical lift bridge in the world. When lowered for trains, it clears the water by 9 meters, but when raised, the span towers 41 meters high, leaving clearance for even the biggest ships.
Over here at the AK Bridge, we have the bridge drop scheduled for 9:45 a.m. You see any problems with that as far as vessel traffic goes?
But for Supervisor of Structures Ryan J. Wagner, it's not all plain sailing. To minimize disruption, the bridge can only be lowered 3 times a day, for just half an hour.
Okay, yeah, I see. There, she's coming northbound, right? I'll call when I know she's clear, all right? Okay, Roger, will do. For our bridge drops here, we have to coordinate with the Coast Guard based on the tremendous amount of vessel traffic coming through the Arthur Kill Channel. We have about a half an hour time frame to get the train over and then to have the bridge back in the fully open position.
Lowering and raising a 2,000-ton lift span in such a short window requires supersized engineering. The bridge is fitted with a powerful system of counterweights and cables, driven by motors installed at the top of each tower.
Security, 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 AK Railroad Bridge coming to a close. Security, 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 AK Railroad Bridge coming to a close.
With all shipping being kept at bay, Ryan is putting this cutting-edge technology into action.
I've enabled the controls. That's enabled power to go to both drive motors. Once the drive motors are fully energized, I give the command for the bridge to go into the span seated position, and then the bridge starts coming down.
All right, here we go. It's starting.
The concrete-filled steel boxes used as counterweights each weigh a whopping 1,000 tons.
You can see the counterweights moving up right now in the perfect balance to the bridge that's coming down. You really want the bridge to come down exactly level. Both the motors have to work simultaneously, and so that there's no skew, so that the trains can go across, and then we can go across.
After just 2.5 minutes, the span enters its final leveling, a critical phase demanding millimeter precision.
So right now you have the bridge going through its skew correction system. We have a variety of sensors that are basically detecting all kinds of positions of gearing, physical track structure like the rails.
If the tracks don't line up, the trains will miss their crucial slot.
If all those checks are not correct, the dispatcher will not be able to allow a train to pass over the bridge. That causes a variety of issues. Train delays, it impacts vessel traffic because now we have the bridge seated and it cuts into our half-an-hour time frame.
With the bridge successfully locked, now the goods trains and Eric can carry on their journey.
All right, we saw it come down, and now we get the pleasure of actually going across it. What a piece of engineering. I'm looking at it now. I see the giant counterweights above. We're on it seamlessly. You can hear the banging and the clashing, and I see the water underneath. What a brilliant bridge. It's really hard to imagine that this is actually 100 feet higher in the air on a normal basis.
The 170-meter shortcut between New Jersey and Staten Island takes a matter of seconds. The race is now on to get the waterway moving.
Roger. So right now we're starting the process for the bridge opening. You have the warning indication to notify anybody that's on the span that the bridge is going to be opening.
Ryan and his team now have less than 3 minutes to open this impossible bridge.
See the counterweight coming down right here, right now. So at this point now, the span and the counterweight are approximately the same elevation.
Over 50 years after it first came into operation, the Arthur Kill Bridge still manages to return to its open position, bang on schedule.
Every day, there's always something new to be learned. There's always something that can be improved upon in terms of its operation to make it more efficient. Yeah, it's certainly something that I enjoy working with.
Every day, the brilliant mechanics of this towering bridge allow tons of freight to be carried in and out of Staten Island.
Without it, there would be no crossing. But with this bridge, the train just went right across. It seems so simple, and yet it's an engineering marvel, and it's really, really gratifying to see it work.
railway crossings. Seemingly impossible structures spanning nature's vast voids, creating huge engineering challenges, demanding inspired solutions to keep our trains running.
It's really exciting. What a brilliant bridge.
Building bridges throws up many problems, and none more so than height. When creating super tall crossings, the solution may appear to be out of reach. Supersizing can work, if your environment allows it. Tackling it from a different angle may be the answer, but can end in calamity. Nestled in the east coast of New Zealand's North Island lies the Mahaka River Gorge. Its extreme landscape perfect for outdoor pursuits. But you would think its towering ravines and fast-flowing river would put the brakes on any railway. However, one bridge builder proved otherwise.
Hey, buddy.
How's it going?
Ah, good.
Cool. Chuck your life jacket on there like a backpack. Good. Make sure you get all 4 buckles up, including the one right down the bottom there.
For heritage advisor Karen Astwood, there's only one way to appreciate how engineers traversed this impossible chasm.
So this is the Mahaka River, and when you look up, you get a really good sense of the huge challenge that the engineers had here. To get the train across this massive gorge, they had to put up a structure which is 350 feet tall, making it the highest in Australasia and the 5th tallest in the world at the time it was constructed. This would have to be a bridge of epic proportions. And here it is.
This is the Mahaka Viaduct.
That is a truly impressive structure. What a stunning piece of engineering. I'm actually a little bit speechless. It's awesome. It's really great. I love that structure.
Spanning almost 300 metres and 95 metres high, the Mahaka Viaduct has conquered nature.
Not only is the Mahaka Viaduct a thing of beauty, the engineering that made it possible is just as impressive.
Completed in 1937, this was a bridge born from an isolated community's critical need. On New Zealand's North Island, the town of Waira sits on the northern shore of Hawke's Bay, perched on the mouth of a major river. A wild landscape that 80 years ago threw up many problems.
Wairoa could be often cut off from the rest of the world for weeks at a time because the basic dirt roads became impassable in bad weather, and also there's a treacherous sandbar out there in the river mouth, making it difficult for even the smallest vessels to access the town.
A rail connection to the city of Napier, 80 kilometres to the south, and Gisborne to the northeast would offer Waira a crucial lifeline.
But construction of this vital link was complicated by a series of shattering setbacks and the immense engineering challenges posed by the North Island's rugged terrain.
And none would be greater than the deep ravines surrounding the Mahaka River. But engineer John Cull believed he could beat the odds with his design for a prefabricated, supersized steel structure. Work started in 1930. With concrete foundations in place, a death-defying workforce nimbly set about its construction high above the valley floor. But the real engineering challenge was getting 1,900 tons of steel to these dizzying, windswept heights.
If you can imagine these two ladders are towers either side of the gorge, then a cableway was strung across the gorge like this. Suspended from the cableway, represented here by these carabiners, was a hook, which moved independently along like this. What this meant is that once you had attached a steel component to the crane hook, like so, it could be moved out into the gorge. It could then be manoeuvred into place and affixed really quickly.
The engineers took this brilliant solution one step further, slinging two cables across the ravine, each one working independently, allowing super heavy steel components to be twisted and swung, positioning them with pinpoint accuracy.
And because the steel components were prefabricated and then brought to site, the viaduct could be assembled like a giant Meccano set, and progress was really, really quick.
Incredibly, Cul's rail bridge was completed ahead of schedule and for half the estimated costs. The Mahaka Viaduct was the final link in the line to Waira, allowing goods and residents in and out of the once isolated region.
Today, Waira is totally transformed. Thanks to one of the world's tallest railway bridges, this once largely inaccessible town has been given a whole new lease of life.
Creating super high spans is a huge achievement, but when it comes to crossing chasms, railway engineers often face an equally taxing problem. Whether traversing channels or seascapes, trains often have to negotiate wide crossings, presenting their structures with a whole host of problems. That can leave engineers all at sea. And it was one such problem affecting Scotland's capital, Edinburgh, during the 19th century. For this booming city, open countryside to the south and west allowed easy access for trade. But to the north lay the Firth of Forth, a vast estuary renowned for its harsh weather and fast-flowing waters. For a railway to overcome this would take a crossing like no other. The Forth Bridge. The largest steel structure the world had ever seen.
Groundbreaking design. Victorian engineers at their best.
Spanning 2.5 kilometres, 53,000 tonnes of steel and 6.5 million rivets ensure this feat of engineering stands strong against the brutal battering of the North Sea.
The engineering that was involved was the very best of its day. The forefront of engineering, the very best of materials, and we've ended up with a magnificent bridge.
It's the brainchild of engineers Benjamin Baker and John Fowler, who tackled the improbable challenge of a 2,500 metre long bridge with a game-changing design. Their solution, based on balance, was to cantilever the bridge. 3 giant diamond-like structures act as centre points for cantilevered arms. A concept best appreciated from an unrivaled view above.
Where we are just now is on the tower, one tower of the bridge. And from each tower, there are 2 cantilevers, effectively like one arm poking out in either direction, stretching out. And these 2 arms are what's called a balance cantilever. So each balances the other one off.
But it wasn't just the scale of the Firth of Forth that threw up problems. In 1879, its predecessor, the Tay Bridge, succumbed to a major storm, Its collapse tragically killing 75 on board a crossing train.
Fowler and Baker learned a lot from the Tay Bridge disaster, and they had to come up with something that was robust and strong.
To withstand the fierce weather and fast-flowing waters called for rock-solid foundations. But in the deep estuary, this was far from easy.
If you can imagine the space between the water to the deck level, you've got that same depth of water below there. So it was incredibly deep water. It was deeper than the North Sea, a lot of it.
Building 12 mammoth cylindrical concrete foundations here would be far from straightforward.
What the general public see is actually very top end. If you think of an iceberg, there's a huge amount of work below this actual masonry here. This is the top of a foundation that goes down 30 feet into the actual bed itself, and that's where the casing was used to actually create the foundation.
The caissons were gigantic twin-walled cylinders floated out and sunk in the estuary. Once pumped out, 20 to 30 men would then excavate the seabed, creating the foundations.
Mustn't underestimate just how arduous and how hard a piece of work that was. Nothing more difficult than digging foundations on the Roth Bridge.
With the underwater works complete, Baker and Fowler constructed enormous piers to take the weight of 2,000-ton trains and over 50,000 tons of steel.
These piers take an enormous load. All the load of the bridge has to come down onto each of these 4 points on each of the 3 towers. The most important part of the whole bridge.
As with everything on this impressive bridge, the solution was supersized.
This is a very special place on the bridge. There's basically very few people have actually been allowed to stand here. Each one of those blocks of stone is a ton. So multiply that by several thousand. That's the scale of one of these foundations, of which we have 12 right through the bridge. Fowler and Baker were at the very forefront of engineering ingenuity. To even imagine a bridge such as this was in many ways risky. Has the risk paid off? No question at all, absolutely.
Extreme crossings, connecting the world's railways in nature's most demanding locations.
Wow, this is amazing!
And one such bridge faced more problems than most. Scotland's Firth of Forth. Home to the staggering 2.5-kilometre long Forth Bridge. Designated a World Heritage Site, this game-changing cantilevered structure is engineering on an epic scale.
If you turned the Eiffel Tower on its end, Eiffel Tower would fit into one diamond. That basically is one Eiffel Tower. So have we got 6 Eiffel Towers? I think we have.
Completed in 1890, its jaw-dropping size is down to a pioneering use of steel, which, unlike its iron-built contemporaries, is super strong, resulting in what was once the world's largest bridge.
Guys, what we're going to be doing this morning is we're taking the safety net out.
Today, however, the 53,000 tons of steel creates an ongoing battle for consultant coatings inspector John MacDonald.
Biggest problem is dropped objects. Can't happen, okay? Everybody happy with that? Yeah. Right, great.
Salt water and 140-kilometre-an-hour winds relentlessly take their toll.
We need to put a scaffold in to give access to a steel worker to come in to do some cutting for us, to do some welding.
With 200 trains a day passing above, it's crucial this crack engineering team maintain the bridge.
All good.
in perhaps the nation's most precarious workplace.
The net is at the moment tied firmly to the bridge, and we're just untying it so we can start to deploy it. It's kind of a curtain system that opens it up. So should we unfortunately drop anything, it will land inside the net. Yeah, good. Good, yeah. Let's have a go. Got a good spot.
Goodbye.
Okay. Try and push it out of that first. We're good on this side.
Although 95% of the bridge's steel still exists, the race is on to remove any unsound metal.
In this part of the bridge alone, I think we have scheduled 190 repairs. They're all small scale, but put together, that's quite a lot of work. The repair itself might take 2 hours, but the logistics of getting to the repair, we could be looking at 4 or 5 men working for a week.
And today, like practically every other day, action needs to be taken.
We have 2 pieces of steel make up this component. This one is in very good condition, except for a bottom corner here, we have just a great deal of corrosion. So we're reaching a point where if we leave it very much longer, this part of the member will actually become detached from the bridge. It will fail. We're going to do the repair. This is a very small repair, but eventually you would start to affect the integrity of the bridge if we didn't do these repairs on a regular basis. And it'll be replaced with a new insert welded in place.
But perhaps this bridge's biggest challenge is seen through its iconic colour.
How many coats is this, Peter?
Second coat.
On this and that one?
Yes.
Okay.
John and his team must keep 230,000 square metres of protective red oxide paint up to scratch.
Squads of men go to a select area, chip away, paint, move on to another area, chip away, paint, because the size of this thing, they were constantly playing catch-up.
But now a new solution, developed from the North Sea oil rigs, is brushing away this problem.
On a microscopic scale, it has flakes of glass suspended in the paint. When it's applied, as it cures, these tiny bits of glass settle down flat onto each other, a bit like the scales of a snake, and make more or less a glass cover over the steel, impermeable.
This cutting-edge paint will last 25 years, safeguarding the future of this magnificent railway crossing.
This bridge is in better condition than it has been for the past 75 years, possibly in the best condition it's been in since it was built. Sometimes you just stand back and look at the structure and think to yourself, it's a privilege to be here.
The pyramids were wonderful. This bridge is wonderful. It's up there. I came along here for 6 months and stayed for 23 years. I just love it to bits.
For any railway bridge to remain standing, keeping it in tip-top condition is crucial. But the key to any super strong structure is getting its design right in the first place. To take the strain of a train, a railway crossing needs support. But not any old support. For bridges, the right geometry is key. And in Germany, over 150 years ago, one rift in the landscape would push bridge design to its limits. At 500 meters wide and 70 meters high, the Gulch Valley in the state of Saxony is a spectacular sight. But as Professor Lutz Nietner is finding out, in the 19th century, it was also a seemingly impossible hurdle for the railways.
In the beginning of the 1800s, the engineers had a task to build a new railway connection between the towns Leipzig and Hof, and their problem was to cross this valley. It's a very huge valley, and the valley sides are very steep, so the trains of the time had a problem that they hadn't enough friction on the rails.
Heavy steam engines of the day struggled on any significant slopes, so building a line down into the valley was out of the question. A bridge was the only answer.
This bridge has to be very enormous span and has a very enormous load capacity to hold all the trains rolling on them.
The bridge would be unlike any other in the world. And even today, for those that cross it,
after the corner, we cross the bridge.
This railway's mind-blowing solution still takes the breath away.
It's a very nice picture, driving over the bridge. I'm lucky. She's the greatest bridge in Europe.
The Gulch Viaduct is the largest brick-built bridge in the world.
So the simple solution is always the best. And that's what you can see here, the Gulch Viaduct.
Stretching 574 metres and towering 78 metres high. When opened in 1851, it was the tallest railway bridge on the planet.
For me, it is a masterpiece of engineering. I love it.
The bridge's extraordinary dimensions are down to one man, engineer and mathematical genius Johann Andreas Schubert. He knew that spanning such massive distances whilst taking the strain of a train could only be achieved by one simple shape.
Schubert was the first engineer who proved the stability of his constructions in a mathematical way on the paper. He relied on the mathematical principle of an arch shape.
For centuries, the strength of this classic shape has defied belief, allowing buildings and even the most surprising everyday items to withstand incredible loads.
On the first sight, an egg seems to be a very fragile thing. If you tap it on a hard surface, it can be easily broken. If you can see here, the egg is shaped like an arch, and we want to try to stack some bricks on them. So this is the crucial point. At this moment, the load from the brick concentrates on these 4 eggshells. Let's see what happens if we stack another one on it. So we have just doubled the forces in the shells of the egg. Let's see if there is a third brick. The total load of all these bricks is concentrated on the 4 points of the eggshells. The load is distributed through the compressive strength of the shape of the egg onto the table. That's what we have in the bridge behind me. The arch shape is an essential element of civil engineering.
With the load-bearing capacity of arches proven time and again, could they withstand lateral pressure like that of a train? Schubert created a mathematical formula proving they could do just that.
Schubert's formula has a very great effect on bridge construction in that time, because he was able to prove in a mathematical way that such a simple design has a very high load capacity to carry rolling loads on top and to transform these tensions into compressive ones.
Safely carrying trains across the enormous Gulch Valley would take 81 arches built over 4 stories. An elaborate design, which also had to be built on a budget. Sourcing materials locally, Schubert's solution was to build with bricks.
It was the cheapest and easiest way to have a material because of the local clay pits here. It was quite unusual in that time to use bridge for such enormous constructions because bricks don't have so much compressive strength. So what you need to do is to combine a lot of them so you have a lot of area to put forces through.
It would take over 26 million bricks to span the chasm.
A normal worker would have to do 1,600 bricks a day. And this is a very challenging work.
After 6 years, nearly 2,000 workers finally completed this record-breaking structure in 1851.
Looking from this point, I feel very small compared to this massive bridge.
Today, this chasm crossing still stands up to modern engineering, as intercity trains travelling at over 100 kilometres an hour glide over its historic arches.
It is incredible what has been built 165 years ago. This bridge is an amazing piece of engineering.
Many of the world's greatest crossings have been built for the railways, straddling deep gorges, traversing wide open valleys, keeping our journeys on track.
It is a masterpiece of engineering, and I love it.
But sometimes the obstacles can appear beyond the bounds of possibility. This is the Orisund Strait, an immense waterway forming a natural boundary between Denmark and Sweden. With its notoriously busy shipping channel and close proximity to an airport, it's the last place you'd expect to find a railway crossing. For centuries, it was only possible to cross by boat, and even that isn't easy.
We have 16 kilometers from Denmark to Sweden, and during wintertime, for example, you can have ice in this area. We've had up to 40 centimeters of ice, so you can actually not go by boat many days during wintertime. So there were days where we couldn't come from Denmark to Sweden.
For many, building a transport link to connect Sweden's Malmö and Denmark's capital, Copenhagen, was just a dream.
It's quite difficult to build because we need to have the road traffic and the train traffic in the same structure. So it's very, very big structures we talk about.
The solution would have to be like no other. The Orisund Bridge, the longest cable-stayed rail and road bridge in the world. At 8 kilometers long, engineering on this scale required around 142,000 tons of steel.
It was seen as one of the biggest engineering challenges. Engineers came from all over the world in order to see what we had done here.
Despite its size, for civil engineer Niels Lukeberg, the biggest challenge was thrown up by its location, one of the world's busiest shipping lanes.
Due to the very large number of vessels passing through Orisund, we had to leave a stretch of water open for the traffic in order to avoid congestion.
The answer? A colossal centerpiece off the Swedish shoreline. Construction begins in 1995. Huge sections of the bridge are prefabricated and towed into position. Out of the water grows a pair of approximately 200-meter-high pylons, built to support a half-kilometer-long span for ships to pass beneath.
This bridge is designed for navigation purposes with a clearance height of 55 meters, so even very large ships can pass through.
However, in this 16-kilometer-wide strait, a shipping passage is also needed off the Danish coast. But here, a bridge is out of the question.
There is a special problem because we have the Copenhagen airport, which is quite a big airport, so close to the strait here. We could not build a bridge on the Danish side simply because the high pylons, they would conflict with the runways.
Remarkably, instead of going over, they now decide to go under. This is a bridge that morphs into a tunnel.
We are just on top of the entrance to the tunnel. The tunnel itself is constructed of prefabricated tunnel elements, which are 40 meter wide and 60 to 80 meter long, floated to this location and submerged into the trench.
We ended up with a 4-kilometer long tunnel. That had never been done in that scale before. It is the biggest immersed tunnel ever constructed in the world.
Digging the trench for this record-breaking tunnel produces 7.5 million cubic meters of material from the seabed, used to create the Orisund's third astonishing landmark. A 4-kilometer man-made island in the middle of the Baltic Sea.
This was an open water area in the middle of Orisund, and now it's an island linking the tunnel with the high bridge and thereby forming a part of the link to Sweden.
Opened in 2000, this hybrid link has transformed the region, connecting two countries together.
Before, it took more than 1 hour just to pass the water, and now it can be done in 7-8 minutes.
Whilst 20,000 cars pass over the bridge every single day, 60% of people crossing take the train. And the shipping lanes continue uninterrupted.
Is it a dream job? Yes, of course it is. I've been on many projects in my lifetime, but this one will stand out as one of the biggest challenges we had and one of the biggest successes we've had for this type of links.
For over 150 years, bridges have opened up the world to trains, allowing them to cross seemingly impossible divides.
We think about technology, but it's the hardcore bridges that are the things that really make everything possible.
Thanks to inspired solutions,
That's a wonderful piece of engineering. It's a wonderful piece of architecture. There's no reason why this shouldn't be here for another 100 years plus.
engineers continue to create their impossible railways.
Bridges are among the most important components of railways all around the world, helping trains reach their destinations by overcoming formidable obstacles that stand in their way.